Hello guys, welcome on Tesla Eduventures. In this video, we are going to discuss the Zeroth Law of Thermodynamics and the first law of thermodynamics. Now let us see the Zeroth Law of Thermodynamics. You can see that there are three gases, gas A, gas B and gas C. This law states that if gas A is in thermal equilibrium with gas B, and gas B is in separate thermal equilibrium with gas C, then gas A and gas C will be in mutual thermal equilibrium also, which obviously proves the fact that if the temperature of gas A and temperature of gas B is same, and if the temperature of gas B and temperature of gas C is same, then obviously the temperature of gas A and temperature of gas C will be same. So this is the Zeroth law of thermodynamics. And you have heard that the Zeroth law was stated after the first law of thermodynamics, but in priority sequence this Zeroth law is given the priority due to the fact that this law states the basic of heat flow, which is the temperature. So this law states that the heat will always flow when there would be a temperature difference. So this is the Zeroth law of thermodynamics, and let's talk about the first law of thermodynamics. So let us talk about the first law of thermodynamics for real gases first of all. So let us imagine that there is a real gas. You can see that there is a real gas, and this real gas is enclosed in a cylinder which has a movable piston, and outside the piston there is atmosphere, and the piston is heavy, it has some mass. Now when we will heat up this gas, when we will supply some heat to the gas, then obviously that heat given to the gas will be utilized in increasing the molecular kinetic energy. Any molecule will start to move with the greater speeds in random directions. So the molecular kinetic energy will increase. That is dUK, which is the internal kinetic energy of the gas. And we know that each molecule in a real gas interacts with the other molecule with weak intermolecular forces, which are attractive forces. So this is a molecule and this is another molecule, and they interact with each other with these weak forces. Now when when this piston is going up, obviously this piston will go up because the kinetic energy of these molecules increased, and the pressure of gas will start to increase, and hence this piston will move in the up direction, and the volume of this gas will increase eventually, and due to increased volume the intermolecular spacing between the molecules will increase, and therefore we have performed some work done against these intermolecular forces which are attractive. So some part of that given heat is being utilized in internal kinetic energy of the molecule as well as work done against the intermolecular forces, and the rest of the part is utilized in work done against the surroundings. You can also see that the surrounding pressure, atmospheric pressure, and the mass mg of this piston is restricting the piston in going upward direction. So there would be the work done utilized in moving this piston in the upward direction. So the heat given to the gas will be utilized in molecular kinetic energy, the work done against intermolecular forces between the molecules, as well as the work done against surroundings. And this work done against intermolecular forces is nothing but the internal potential energy of the gas. So we can say that the heat given to the gas is utilized in internal kinetic energy as well as internal potential energy as well as the work done against surrounding. Now this internal kinetic energy is directly related with the temperature of the gas. Now for real gas, we know that the most important difference which we studied in assumptions of kinetic theory between the real gas and between the ideal gas is the fact that the molecules of an ideal gas do not interact with each other with some force, apart at the time of collision. We are not talking about the collision at this point of time. We are just talking about the molecular interactions. So there are no molecular interactions in the molecules of an ideal gas, which means that there would be no internal potential energy in this ideal gas, and the heat given to the ideal gas is utilized just in the form of the internal kinetic energy of the gas, as well as the work done against the surroundings. And we have already studied and discussed in the assumptions of kinetic theory of gases that the internal energy of the ideal gas is internal kinetic energy, and kinetic energy does not depends on a reference level. So we can say that kinetic energy is absolute quantity, but potential energy depends on the reference level. So we can say that potential energy is a relative quantity. So the internal energy of a real gas, which also contains the potential energy, is a relative quantity, and the internal energy of an ideal gas, which is just the internal kinetic energy, is a absolute quantity. Now there are some sign conventions which you need to remember, and there is a slight difference of sign convention for work done in physics and work done in chemistry, thermodynamics. So you should not get confused with that difference. You should just concentrate on the sign conventions of physics. Now, according to these sign conventions, if heat is given to the system, or if heat is given to the gas, which means that if gas absorbs the heat, then dq is positive. If gas releases the heat, then dq is negative, first of all. Other thing is the fact that if the temperature of the gas increases, then the change in internal energy is positive, and if the temperature of the gas decreases, then change in internal energy is negative. And if gas is expanding, then work done by the gas against the surrounding dW is positive, and if gas is compressing, then work done by the gas against the surrounding is negative. So this was the first law of thermodynamics for real gases and for ideal gases, and Zeroth Law of Thermodynamics. In the next video, I'll be bringing some more concepts of thermodynamics. Thank you.